before I did. And I don't know how much, I mean, you need to know about three-phase power for any kind of electrical or computer engineering, but you'll need to know it more for EE than for computer engineering.
Right.
All right, so since y'all did start this in class, some of this is going to seem, or it should start off fairly familiar. So I have this first page just for you to look at and to kind of crystallize the different, the two different types of three-phase circuits. So we have the Y configuration and the delta configuration. Did y'all do Y and delta in circuits 1?
Yeah.
Okay.
That's right.
Where is my Adobe? Not open. Is it under this? That's Word. I'll just grab it. Oh, can you not rotate in OneNote? I don't think you
Like you hover your
can.
mouse like right outside one of the boxes, it gives you like a little rotate symbol, like the white ones.
Seems like you should be
If you
able to.
right click it, does it give you like a rotate option?
Yep, there we go. Rotate left. All right, so either your source or your load can be in Y or delta. So usually you'll find it easiest if you have it in delta to change it to Y, and that's what he typically does in his examples. And I think, and that's what he would be expecting, and that's how he would grade it. So let's take a look at the difference between Y and delta and what the different notations are so that you can recognize them when you see them. But it's weird that it doesn't have like a little rotation thing where you can just free rotate. That's kind of odd. Okay, all right. So first you have the nodes that in your source circuit you use numbers. So your source is going to be where you have your power. And so if you look at I just have the B pulled up here that has a Y source and a delta load. If you look at the source, we have the nodes 1, 2, 3, and N. And N is a neutral node, and you only have the N node for a Y. You don't have an N node for a delta. But if I had a delta source, I still have my nodes are still 1, 2, and 3. So the numbers, and this is just convention, so the numbers are 1, 2, and 3. Now in your load, your nodes are A, B, and C. And then you'd use a capital N for the neutral node for a Y, a lowercase n for the neutral node for the source. So 1, 2, and 3 are nodes in the source circuit. So just, if you want to, you don't have to write these, but that was the intent for the worksheet where I have this table. So 1, 2, and 3 are nodes for source. A, B, C are nodes for load. N and N are neutral nodes for Y only. I swear I turned off capitalize in first cell of table. Maybe it was my other computer. Okay, so all right, so that's what those are. All right, so now let's look at the different ways that you talk about voltages. So if you have capital V1, capital V2, capital V3, these are the phase voltages of a Y source. With RMS magnitude you can call it V Y V sub YS if you wanted to, but it's the RMS, the kind of magnitude of the voltage for the Y source. And when we talk about the phase voltages, if we look at our circuits here, so this would be Y phase, this is source, Y source. So if you just look, they're just V1, V2, V3. They're just voltages the way you've always done them, where the value of V is the voltage on the positive side minus the voltage on the negative side. And the negative side is always neutral. And so that you have that set up so you're always comparing them to this neutral node. And that's going to make them different from the phase voltages of the delta source. So something that looks like V12. Not that. V12. There we go. Is the phase voltage of a delta source. Yeah, it comes in handy. And with RMS magnitude, unfortunately, I don't have a language that has a square root alphabet. I'm just going to type square root. Well, already here.
If you do Windows P and period.
Windows period?
Yeah, it brings up this menu of like, oh no, that works. There you go.
Windows period?
Brings up a list. You go with the symbols one on the right. Yeah, to the left of the last option. Just like that one. That's like every.
Nice. Okay, how am I going to remember that?
Right side. There's a math one. That's the.
Okay, so hold on. That has to be remembered. Did you know if you have a document that's like full of hyperlinks, if you select all and do Shift Control F9, it deletes all the hyperlinks. So this is Windows plus period brings up All right, so, and the magnitude is going to be the square root of 3 of the voltage of the equivalent Y network. So the delta voltage is square root of 3 times the Y network, but notice the delta network, you're talking about the voltage between two sources, whereas with the Y, you're talking about the voltage between the source and the neutral node. Now, the neutral node, not surprising, we're calling it 0, so that's ground. VAB, VBC, VCA, those are line voltages. Okay, so those are line voltages, and that's voltages between transmission line pairs. So if we look at this, you see VAB, VBC, the line voltages. Those are the voltages between the lines. They have the RMS magnitude VL. So all of these have the same magnitude. They all have magnitude VL, and they're the same as the phase voltages of the delta load. And so So, so when I've got my delta configuration, if you look at these lines, so look at line line L3 and line L1, what would the voltage difference be between those two lines based on our delta load?
ZCA?
Yeah, because we have A, they're at A and C. So, yeah, does that Make sense?
Right.
Yeah. Now let's look at the Y load. So if I have a Y load and I want to look at the difference between the voltages, then I would be comparing it to ground. And so that's why on the next little entry on this table, you have the N, because if I look at this load here, then the voltage between this top line, line 1, and N is VAN. Now, notice capital N and lowercase n are both 0. I mean, so they're the same thing, but we just use the capital N when we're referring to the load. Okay, so VAC line voltages, magnitude VL, and same as phase voltages of delta load. All right, and then the bottom, the last one here, the VAN, VBN, VCN, those are the phase voltages of Y load. When we say line voltage, that's shorthand for line-to-line voltage. Because what would it mean to just say voltage? Voltage is always relative to something else. You don't have, I mean, if you're talking about absolute voltage, that's usually like in a physics class where you're saying you're comparing it to the potential at infinity. Anytime we talk about voltage, we're talking about reference to something that we set as ground or to something else. And when we say line voltage, we're talking about line to line voltage, so VAB, VBC, something like that. Line voltages are voltages between transmission line pairs. So when we say line voltage, we mean transmission line pairs. What do I mean by transmission line? What is a transmission line? Like in one of these?
The wires going from the Y to the Y and the delta to delta Y.
Yeah. And you have associated line currents. So when I'm talking about the line voltages and line currents, I'm talking about these transmission lines. And when I say phase, I'm usually talking about voltages and currents across the impedances. But you need to be careful because not everybody is consistent with that. So you should say whether you're talking about the source or the load. But typically, so just keep that in mind. Okay, so look at your diagrams and see if you can identify what these different currents are, and then tell me when you think you have one.
So the single numbers are the currents through the voltage sources on a Y configuration.
Okay,
The two numbers are voltage sources on the delta configuration.
so on the source or the load?
The source.
The source, yeah. Okay, so single number. So I1 current in Y. And I12 is current in delta. And we're talking about the source. And so if you look at the Y over here, so we've got I2 is the current through the branch going to node 2. So it's going from the neutral to the node is the way it's defined, so from N to node. And then in the delta, I12 means going from node 1 to node 2. All right, and then IL1, IL2, IL3. Would be our line currents, and if I have IL1, IL2, IL3, are all of these labeled that way? Yeah, now notice that if I have Y to Y, and this is why we like Y to Y, I1 is IL1 is IA, and I2 is IL2 is IB. But if I have delta, I have from my Y source, I have I1 and IL1, that's fine. But then I get to A, and I've got two currents coming to A. And so it doesn't, it's not all the same. And if I have a delta source, then IL1 is actually going to be I31 minus I12. So that just makes it a little harder. That's why it's always nice to convert them to Y. And IAB, IBC, ICA, those would be our currents in a delta load. So the letters let you know it's in a load. If it has two of them, it's going to be in a delta because it's going from one node to another. So IL1 is a line current in in Y. It equals I1 equals IA. And IAB is current in a delta load. Okay, and then impedances, we have Z, TL1, TL2, TL3. What do you think those are going to be? We pretend like it's 0 a lot of times in class.
The wires.
Yeah, those are the impedances of the transmission lines. And you'll find when you take power that when you start talking about real power and real power lines, these impedances become important because, it's not zero resistance to, transmit power over miles and miles and miles. So these become important. You're probably not going to have to deal with them in this class. But ZTL1 equals impedance of transmission line. Yeah, because we always act like our wires have zero impedance. And so Zn would be the impedance of the line to neutral in a Y configuration. And all of these things become very important in real power. And then ZA, ZB, ZC are the impedances of a Y load. Since you just have one letter, it's a Y. And ZAB is the impedance of the delta load. In almost all of the problems you're going to have to do is you're almost always going to have a balanced load. That's what you want. And I don't think he's going to give you one that's not balanced. We might have an example of one, but it's not going to be a big problem from beginning to end with an unbalanced load. It might just be, set it up for an unbalanced load. So a balanced load, the impedances are all equal. Okay, so how do you convert from Y to delta and delta to Y? So hopefully yours will be balanced, and so you just have to do one of them. And if you notice, if they're balanced, it's actually very easy because everything's the same, and these simplify to Z delta equals 3ZY. And that's if it's balanced. Now, if it's not balanced, you have these formulas. Yeah. Okay, so now let's talk about a positive phase sequence and what that means. So if I have a balanced Y source, I have my magnitude of the voltage, and that's here as VYS, and it has its phase phi1. And a positive phase sequence has phi1 is V1, and then subtract 120 gets V2, and add 120 and you get V3. And so you can see that done other ways because you can also have, did I not bring all my notes? I did. You can also have the following. So let me, because this gets confusing because you'll see it both ways and you'll say, well, wait a minute, which is right? And you just have to hope your grader knows. Okay, so let's say I have a y source. Another way I could say this is V1 is VYS and whatever its phase is, and then V2 is VYS, and subtract 120, and V3 is VYS, and subtract 240. So I'm subtracting 120 each time. So why is that okay? So I start here, and I subtract 120, and I end up here. No, that's adding 120. Hold on, let me make sure I get it. Yeah, no, I was right. Okay, that's subtracting 120 because we measure positive angles. Positive angles go counterclockwise. So that's subtracting 120. Adding 120 ends up here. Subtracting 240 ends up in the same place. So they're both positive sequence. So they're both positive sequence. Yeah. So negative phase sequence. Well, what do you think negative phase sequence would be? So V1 would be just angle phi. V2 would be phi plus 120, and V3 would be phi plus 240, or phi minus 120. You're just going around the other direction. But you'll be using positive phase sequence for this class. Now, if I'm looking at my balanced delta source, and I want to figure out what the equivalent delta is from a y. So I have a y, and I want to get the equivalent delta. So this would be y2 delta. V12 would equal V1 times the square root of 3, and you advance the angle by 30 degrees, so plus 30. So you'd add 30 degrees to the angle. So, for instance, if my y was magnitude 100 and angle 45 degrees, so let's say this was V1, then, and I'm in positive sequence and it's balanced, what would V2 be? That sounds good to me. Wait, is that 120? 45 minus 120?
Oh, I did minus 180.
Yeah, I want minus 120.
Maybe 115? No,
I can't do it. This shouldn't be this hard, but luckily we have calculators.
Negative 75.
Negative 75. And then I'm going to choose to add 120 because I can add 120 to 45 and get 165 degrees. Okay, so if that's my y, then what would my delta be? The equivalent delta. So you multiply by the square root of 3, which square root of 3 is 1.7 something. So this would be 170. 173, and angle 75 degrees, that would be V12. V23 would be 173 angle -45 degrees, and V31 will be 173 angle 195 degrees. Ooh, I don't like 195, but I'm just going to leave it. This the instinct is that's over 180, but I'm not going to worry about it. Okay, and then conversely, if you have a delta source and you need a y, which is what you're more likely going to need to do, you would divide by square root of 3 and subtract 30 degrees. Okay, so let's take a look at these concept questions that I have. So I have concept question 10.1. Okay, so do we have any idea why the voltage sources of a three-phase source are separated by 120 degrees?
It's on the generator. There's 3 magnets 120 degrees off from each other in the circuit.
Yeah, okay, so how do we actually do this? We have three stationary coils spaced evenly, so that would be 120 degrees around in a circle, and you spin a magnet around them. Actually, you spin a magnet inside them. And that's how we make electricity. So they have the induced voltages will have the same amplitude, they'll have the same frequency, but their phase angles are going to be staggered by 120 degrees between them, all of them. Okay, so in a Y source configuration, each voltage source is measured across one of the generator's 3 coils, with one terminal serving as a common neutral for all 3. How are the sources of a delta configuration measured? So if we look at, I saw it on your handout that he gave y'all, you had, y'all had one that looked like this, or am I making that up?
He showed it in class.
Okay, so let me just show you, let me draw it. So you have this, and you have these coils. Oh, it's been a long time since I took power, but this is, and you deal with like what you put inside of these coils. So you have these coils, and you have so they are connected like that, and this is going to be a Y. We'll have N right here. You could actually do it either way, it doesn't matter. And then here's my magnet, and it's going to spin with some angular rotation, omega, probably a frequency of 60 hertz. And if I am measuring a Y voltage, then I'm measuring the voltage of this coil relative to this neutral. If I'm measuring a delta, I'm measuring the voltage of this coil relative to that coil. So if I call this 1, 2, and 3, so for delta, you measure voltage between, for instance, 1 and 3, and for y, between 3 and neutral, for instance. That's how you measure it. But you see, you could measure it either way. All right, concept question number 3. What is a balanced source, balanced load, balanced network? So what do you need to have a balanced source? So what do you think has to be true of the voltages?
They're all equal in RMS value.
So voltages have the same magnitude. What about frequency?
I forget how to say it, but they should all like have the same like period.
That's this. So if they have the same period, they have the same frequency. So they have the same magnitude and frequency. So they have the same period, they have the same frequency, they have the same angular frequency. Because if you think about it, and except for when we did the Bode plots, usually when we had a circuit, there was only one frequency. We didn't usually mix frequencies. Okay, what about their phases? Are their phases equal?
120 off.
Yeah, their phases are separated by 120 degrees. And it doesn't matter if it's positive or negative sequence, that's still balanced. Okay, so that's a balanced source. How about a balanced load? What has to be true for a balanced load?
I guess they all have the same impedance.
Yep, good. So balanced load, identical impedances. So what do you think would make a balanced network?
Balanced source and balanced load.
Yeah. What about anything else? Oh,
Balanced transmission line.
yeah. Yeah, if we wanted to be extra careful, if we're just balanced network, balanced source, load, and identical transmission lines. And that actually ends up being really tricky because that means that, if this is a large network, you have to have your lines, all have to have the same length. Okay, and the next concept question is really just kind of a convention question, just to make sure that you know what we're talking about. When we say line voltage, what are we actually referring to? Because there's lots of voltages, and we say line voltage, what are we referring to?
Transmission lines.
Yeah, it's the voltage across transmission lines. which then, once you know that, you can work backwards to see what that means for the circuit you're talking about. So like on like if I have a Y load, then it'd be the voltage between two of my impedances. If I have a delta load, it's the voltage between two of the nodes. But regardless, when I say line voltage, I mean the voltage across the transmission lines. All right. For which load configuration are the phase voltages the same as line voltages? Phase voltages the same as line voltages. So, when we're talking about phase voltages, we're typically talking about the load. Yeah, that car was here yesterday too. That car's always trying to park up here. It's a hydrogen-powered car. Y'all weren't here. No, y'all weren't here yesterday. No. It has to come into its little parking garage at nighttime.
Why does it have Shell on it if it's hydrogen powered?
I've now told you everything I know about that car. Okay, so when I talk about the phase voltages, we're typically talking about the load. And so if I look at a delta load, then I can see that the phase voltages, which would be like the voltage between A and C or the voltage between A and B, those are going to be the same as the line voltages. So for which load configuration are the phase voltages the same as line voltages? That'd be for a delta load. For which load configuration are the phase currents the same as line currents? It's going to be Y. So you see the line current and the phase current are the same. And then concept question 6. What is the magnitude of IN in a balanced Y configuration? Let's find a balanced Y configuration, okay? This is a balanced Y configuration. So you do have, I think you have, if I had,
All grounds should be connected.
yeah. So if I had a wire right here and it does, that would have some impedance. What is IN in a balanced Y?
0.
It should be 0. Did I give y'all 7 questions? Or just 6?
Yeah,
Six.
just so.
What conditions must apply in order to use the equivalent single phase method? So the single phase method, I haven't talked about that, so let's talk about that first. So what you want to do when you have one of these problems is you want to change it to a single phase. And the way you change it to you change it to 3 independent single phase circuits. And the way you do it is if you have a YY, you're good to go. If you have Y delta, you change the delta load to a Y load. If you have, and you change the load using Z delta equals 3ZY. If you have a delta Y, so your delta is a source, you change your source to a Y using this method right here, where we said to change a delta to a y, you divide the magnitude by square root of 3 and delay the phases by 30. And if you have a delta delta, you transform both the source and the load to y configurations. So what would you need to have in order to do this? It's kind of like I told you wouldn't have any that weren't like this. Balanced. Yeah, it needs to be balanced. If it's not balanced, you can't do this because these things don't work. Because, like, this is not going to be true if it's not balanced.
Oh, right.
Yeah.
Of course. I got you.
So you could still do it. You could, but you can't. I don't know what all would get thrown off. So now what the benefit is that it really simplifies the analysis, and then it just makes it a lot easier to work with. So that's what you want to do. Now the question I didn't ask is, why do we do three-phase in the first place? And the answer is, if I just had a single source and load, what does my power, like if you were to graph the power, what would it look like?
Power for what?
Just in general, what does AC power look like?
Keep it up power for the measurement, probably.
Yeah, but what happens if you have a balanced three-phase configuration is that the power does not oscillate. It's very steady, and so that makes it, easier to use. Kind of, y'all have heard about the battles in the early days of electricity between Edison and Tesla about whether we should have DC or AC.
I don't know about it, but I've heard about it.
Yeah, it is like very, very heated, about whether you should have AC or DC, and they come up with all kinds of ways to minimize the difficulties with having AC. AC is a lot easier to transmit over long distances. You can't transmit DC over long distances. Or I don't know, I say you can't by now. I don't know what modern world does all kinds of things. So, okay, all right, let's take a look at this first example that I have here. I normally only go to 4:30 on Thursdays, but I have a little extra today, and I can go a little bit longer if y'all have time. Okay, all right. So I have that VYS is 120 RMS, frequency 60 hertz, and that's going to be typical. We do have an impedance on our transmission lines, 1 plus J1 ohm. Not very high, but we have it. And ZA equals ZB equals ZC equals 29 plus J9 ohms. Okay, develop a node voltage equation for Vn, the voltage at node capital N with node little n treated as the ground reference. Okay, so looking at node Vn, what currents do we have going out?
We have a neutral current going
IN. And what currents do we have coming in?
I line current 2, 3, and 1.
Yeah,
Those are transmission currents, right?
yes. Um, Now, if we wanted to, we could write those as V big N minus V little n over Zn minus V big N minus V1 over ZTL1 minus Vn minus V2 over ZTL2 minus Vn minus V3 over ZTL3 would equal 0. All right, so now if we have a balanced network, we are now going to try to determine what the line currents are. So, oh wait, this is not right. Can y'all tell me what I left out by accident?
Equal 0.
No, I got the equal 0. I got equal something. Do I have the correct impedances for my transmission lines? Does it include? It doesn't include. I included this impedance, but I forgot to include the other impedance. So this should have been. Let me write it neater. So it should have been V big N minus V little n over Zn minus V big N minus V1 over Z transmission line 1 plus ZA minus Vn minus V2 over Z transmission line 2 plus ZB minus Vn minus V3 over Z transmission line 3 plus ZC equals 0. But what's nice about a balanced load?
The impedances are the same.
Yeah, all those impedances are the same. So if I took all those minuses to the other side, then I would have Vn minus Vn over Zn equals, now I would have Vn, so they all have the same denominator, which would be Z transmission line plus Z, I'll just call it ZL for Z load. So I would have Vn, and then I would have see if I take this to the other side. They're all minus. Where did my minus go? I'll worry about it in a minute. So I get minus V1 minus V2 minus V3. Oh, I guess it doesn't matter because they're really magnitudes, and when I put the minus on it, I would just be changing the angle. And then, let's see. This would be Vn minus Vn over Zn times Z transmission line plus ZL equals Vn times minus V1 minus V2 minus V3. All right, now, if I have V1 equals capital V angle 0 and V2 equals capital V angle 120 and V3 equals capital V angle 240. Well, this, I'm sorry, this is minus 120 and this is minus 240 or plus 120. This is, how do you convert from polar to rectangular?
Cosine and sine.
Yeah, so this would be V cosine negative 120 plus JV sine negative 120, and this would be V cosine positive 120 plus JV sine positive 120, and this is just V. Now, what's true about the sine of an angle and the negative sine of an angle?
Opposite.
Those are opposite. So if I added all these together, those would cancel. What is the cosine of 120 degrees?
Negative half.
It's negative a half. So this, if I add these three together, I get V minus a half V minus a half V, which is 0. So if you have a balanced network, the sum of the voltages is 0.
Oh, okay.
Okay, so yeah, so that was to prove it to you. Now you know it.
That's why.
Yeah, and that's why. Because to me it was not at all obvious, because they have all the same magnitude, and you're like, okay, so why does adding them give you 0? And the reason why is because when you have these phase differences, the way they're going to line up is going to be just right so that they line up to cancel each other out. Okay, and what are we hoping is true about Vn for a balanced network? 0. So now if I look at the equation that I had up here, did I just prove 0 equals 0? I did. Well, okay.
I don't think it's Vn times that. I think it's
Oh, it's
3
plus.
Vn minus V1 minus V2 minus V3.
It sure is. Thank you. That helps a lot. That helps a lot. Yes. Yeah. Yeah. I still have 0 equals 0. Okay, but let's take a look at our individual line voltages. So IL1 would equal V1 minus Vn over ZTL1 plus ZA, and we actually were given some numbers for this. So this would be 120, I think we started at angle 0, 120 over, yeah, so our source is 120. So let's write them out. So if V1 would be 120 angle 0, you might as well start at angle 0, and then V2 would be 120 angle negative 120, and then V3 would be 120 angle positive 120. And then our transmission line was 1 plus J1, and our impedance was 29 plus J9. So when I add those together, I get 30 plus J10. And then IL2 would be 120 angle negative 120 over 30 plus J10. And IL3 equals 120 angle positive 120 over 30 plus J10. So all of this work up here, again, was because it said develop a node voltage equation, and we did, and we ended up with not getting anything out of it. But that's because everything is balanced. But to determine the line current, so now we're doing part B, that's actually easy. And so you just have to do these divisions. And
So our neutral node ended up being 0 because of it being balanced?
yes,
Okay.
yes,
And that's always the case for balanced
yes,
configurations?
yes it is. And this ends up being, I believe, 3.8 angle negative 18.4 degrees amps. And L2 ends up, should be the same magnitude, and it is 3.82 angle negative 138.4 amps, and IL3 is 3.82 angle 120 plus, so that'd be 101.6, yeah, 101.6 degrees amps. These are in RMS. What if I wanted to write them in the time domain?
The magnitude, cosine.
Also remember they're RMS.
Square root of 2 times magnitude cosine omega t plus the angle.
And that was 2, and 2 I had negative 138.4. So I just did one of them. And then you do 3 and 4 the same. I mean, 1 and 3 the same. And then part C said, what was part C? Part C was determine line voltages VAB, VBC, and VCA. How would we do that?
Voltages.
Mhm. So I want the voltage between line 1 and line 2, for instance, which would be VAB.
You could go, we have the currents, so you could go from in across the load to A and find the
Mhm.
voltage drop, and do the same for B,
Mhm.
and find the difference.
Now notice you have to be a little bit careful here because our ground is right in the middle. So it would end up, so VAB would end up being IL1 ZA minus IL2 ZB. Because we would have the voltage from A to B would be the current going in this direction times this impedance, okay? And then the current going in this direction times this impedance, but IL2 is going in the other direction. So I had to turn it around. And then you would just use the values that you had. And so if you want to go back and do this on your own, VAB ends up being 200 angle 28.8. Now, what do you suspect the magnitude of VBC and VAC is going to be?
Equal.
200,
Right.
and then the angles are going to be 120 apart. Okay, so I didn't get to any of the problems, but if you look at them, they're really not that bad. If you wanted to try them on your own and then ask me if you got them right, I'd be happy to check them for you. Or I might do them on, surely today is like Friday already, right?
Pretty much.
Yeah, okay. Yeah, so, but I might do them on Thursday. Okay, so was that